Feel Good Hemp is the first and only brand to offer high-quality CBD oil products alongside a free platform that offers proven self-help and self-healing techniques, all to help you feel good naturally. Feel Good Hemp was started by Noah and his wife Danielle after they used hemp oil and other techniques to save Noah's father from a terminal cancer diagnosis. Now, I heard this story firsthand when I interviewed Noah. It's a real good one, and it's probably the most heartfelt and compelling story I've ever heard about why someone started a CBD company. So Feel Good Hemp is more than just a great place to buy CBD products. It's actually a community of like-minded souls committed to feeling good and doing good. So use coupon code GENIUS33 at checkout to save a third or 33% site-wide on your first purchase. Visit feelgoodhemp.org to shop now and access their free empowerment platform.
Forget frequently asked questions,
common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
go above and beyond.
They become very good at what they do, but only
0.1%
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast
with Richard Jacobs.
Hello, this is Richard Jacobs with the Finding Genius Podcast and the Good Question Podcast. I have Patrick Frank. He's a scientific affiliate at the SLAC National Accelerator Laboratory at Stanford University. What we're going to talk about is his own opinion and experience that has nothing to do with SLAC or any of his other affiliations, just so you know. We're going to talk about climate. So, Frank, thanks for coming.
Thanks. I'm happy to be here, and I'm actually honored to be chosen.
Oh, good.
So it's a great opportunity, and I appreciate it.
Yeah, no problem. Well, tell me a bit about your background and how did your attention come to climate?
Okay, I am a physical methods experimental chemist. My education is bachelor's and master's from San Francisco State University and a PhD from Stanford University. I have postdoctoral training at the Weizmann Institute of Science in Rehovot in Israel. And I've spent the greater part of my career as scientific staff at SLAC National Accelerator Laboratory and at the Department of Chemistry, Stanford University, kind of a joint appointment. So I had a number of different hats there, carried out my own research program as well in association with my supervisors that involved the study using the X-rays that SLAC generates to study trace metals in biological systems mostly. So it's a lot of detailed physical analysis and where you have to pay attention to absolutely everything to make sure that your data are accurate. So that's my own personal background. And the way that I got into the climate business was all the way back in 2001 when the third assessment report came out from the IPCC. And there was a lot of accusatory polemics that came up immediately in the press about it. And I got tired of that really quickly. So I just decided I'd read the primary literature and find out for myself whether or not there was something to worry about there. And it took a couple of years of study. And I eventually ran across a paper. I'll actually read you the title of it. It's a paper by Willie Soon, Sally Baliunas, Sherwood Idso, Kirill Kondratev, and Eric Posmentier. And it's called Modeling Climatic Effects of Anthropogenic Carbon Dioxide Emissions, Unknowns and Uncertainties. So this was a paper from also 2001. And what it does is it talks about all the errors that climate models make when they try to simulate the climate, simulate the ocean, simulate the atmosphere, simulate the ice fields, and so on. And the models make enormous errors, hundreds of watts per square meter error. And it's clear that the errors were much, much larger than the effect that the models are being used to resolve. And so as soon as I read that paper, it was immediately obvious that the IPCC could not possibly know what they claimed to know.
What was an example of an error rate and what percentage of the actual measurement was the error rate?
Well, one of the things that they have to simulate is how the ocean works and how the ocean exchanges energy between the tropics and the poles, for example. And the amount of energy that flows north and the cold water that comes south is a huge energy conveyor that transfers heat to the poles where it's radiated away. And the errors are running around 40 or 50 watts per square meter just in that alone, part of that. And that already is about 1,000 times larger than effect that carbon dioxide has on temperature. And so,
the error rate is 1,000 times the potential effects, how could you ever get a clear estimate?
That's exactly it. It's like trying to see an ant through Coke bottle lenses, that can do nothing better than see a cat as a big fuzzy ball, and they're asking you to look at an ant. It's like that. And so there's just no way that they could resolve the impact of CO2 on the atmosphere, because the impact is so small compared to the errors that the model makes that it's just completely undetectable. So that was a real eye-opener to me, and I realized immediately that error analysis is something that needs to be paid attention to in climate modeling. And when I started, that was one of the scales fall from your eyes kind of experiences. And so I started reading climate modeling papers with that view in front of me, and quickly realized that none of the climate modeling papers actually analyze the errors properly. And they don't talk about them at all. And that was another huge surprise, because as an experimental scientist, you really have to pay attention to errors. Otherwise, you don't know what you think you know. And they weren't doing that at all. And so I can talk more about that.
So what are some of the major projections that are riddled with error, and what does that do to the projections? Like, what are some examples, in terms of sea rise or CO2, et cetera?
So the major thing that everybody's excited about is the projected change in air temperature, right? It may go up by 3 degrees. Some people say it will go up by 10 degrees by 2100. And so the error that I focused my attention on was the error in simulating the amount of energy that's in the atmosphere. Climate models have to do that. In order to determine the air temperature, they have to be able to simulate the energy distributions correctly, which includes the amount of energy that's in the air, the troposphere. That's, the atmosphere all the way up to 11 kilometers. And so that's what I focused on, because that's where air temperature comes from. And what I found was that the simulation error that, all these different climate models, there are something like 44 of them now. The average error that they make in simulating the amount of energy in the atmosphere, the minimum error is plus or minus, I'm going to get technical here, plus or minus 4 watts per square meter per year. That's the average annual error that climate models make. And the average...
Well, what's the total estimated amount of energy per, in watts per square meter, so we get a sense for the size of the error?
The total amount of energy is petawatts. It's huge amounts of error, but the energy in the atmosphere is controlled by the clouds. The clouds play a huge role in how much energy gets from the sun down to the surface of the Earth. The total amount of energy coming in from the sun is about, at the top of the atmosphere, is about 1,360 watts per square meter. That's called energy flux. And the amount that actually gets down to the surface is about 245. So that means that about 1,100 of those watts per square meter are reflected away by the cloud tops. And so it doesn't take much changes in cloudiness to change the amount of energy that gets into the atmosphere and gets down to the surface. So
how much reaches the surface depending on albedo, cloud cover in various spots? What's the range?
The range is pretty high. On a clear summer day, in the tropics, if it's a clear day and there's no clouds overhead wherever you are, you can get, something like 1,200 watts per square meter coming down, because there's no clouds to reflect anything away. In Arizona, for example, it can be 1,100 watts hitting the ground on a clear summer day. If it's cloudy overhead, the amount goes way, way down, because most of the energy just gets reflected away. So,
but again, how much energy per square meter? How many watts?
Well, the average is 240.
It's very cloudy versus.
Well, if it's really cloudy, it might be, say, 100 watts per square meter. And if it's really clear, it might be 1,000. So it can vary by a factor of 10, depending upon where the clouds, whether there's, you're in a cloudy day or a sunny day. And of course, depending upon your latitude. Does that make any sense for you?
Okay, so between 100, I understand, but you're saying it's between 100 watts per square meter and 1,000 watts per square meter at the surface, depending on elevation, cloud cover, and a whole bunch of other factors.
Yeah, something like that. I'm just
the error you said was what, 4 watts per square meter or more?
So what happens is that when climate models simulate the global climate, they have to simulate the clouds. And it's complicated business, but there's a notion called long wave cloud forcing. And long wave energy, that's what they're talking about, is thermal energy. And that's the energy that plays a direct role in determining air temperature. long-wave thermal energy flux. And so that's what I started paying attention to in the atmosphere, because it's a direct determinant of air temperature. And I wanted to know whether or not the air temperatures that they're projecting are reliable. So the total effect of clouds in terms of cloud forcing is about 25 watts per square meter. And that means that clouds have a complicated effect. They not only reflect sunlight back from the tops, but they reflect thermal energy back down to the ground from their bottoms. So they have a cooling effect from the top and a warming effect from the bottom. And then the difference between those two is the total cloud effect. And the difference is about 25 watts per square meter. So that's the net forcing that's due to clouds that contributes to the thermal energy of the atmosphere.
So in what's also the diurnal and the seasonal variation, in a given spot? What is that range?
I can't really tell you what those kinds of ranges are, that kind of specificity. It's going to vary enormously from latitude to latitude, and also from summer to winter, and, with the weather, all sorts of things. So it really isn't going to tell you very much to worry about something like that. You can think of the Earth as a kind of...
Well, this is an issue because I have a whole bunch of people, I've interviewed a whole bunch of folks, and no one is able to give me any baseline or any estimates or any ballparks. So therefore, if people putting out papers and modeling, if they can't say this is the approximate variation and this is what we're seeing, then how can the model be relied upon?
Well, what you have to realize is that the Earth varies on a small scale all over the surface, all day, every year. And if somebody wanted to actually sit down and figure out what the insolation was at every single point on Earth, which is what you're talking about, I think, that would be an enormous undertaking. It would be very, very difficult to do that. And as soon as you finished making all those measurements, if you could manage to do it all in a day, say by satellite or some amazing method, the next day it would be all different. And so people do is they say, okay, over a period of a year, say, all of that stuff mostly averages out. Sometimes it's a little cooler here, sometimes it's a little warmer there, sometimes it's a little cooler there, and sometimes it's a little warmer here, and it averages out over the course of a year or so. And certainly gets close to averaging out over 30 years, which is the usual climate minimum time. 30 years of averaged weather is supposed to be climate. So there's a lot of average taking in order to smooth out exactly the kind of thing you're talking about.
Supplementing with hemp CBD products is one of the best things you can do for your overall wellness, or to improve conditions like chronic pain, sleep issues, anxiety or depression, or other conditions related to inflammation. Feel Good Hemp offers high-quality CBD oil products alongside a free platform of proven self-help and self-healing techniques, all to help you feel good naturally. They're offering our listeners a very generous 33% off their first purchase. Use the coupon code GENIUS33 at checkout, and you'll save 33%. Visit feelgoodhemp.org to shop now and access their free empowerment platform.
I'm not taking an issue with you, but again, if someone says to me, oh, sea level is rising and we're in trouble, and then I ask what's the normal variation, they don't know, then how do they know sea level is rising?
Oh, well, we do know.
Carbon is increasing. I just, that's why I'm asking you, have you seen, what numbers have you seen? Because I haven't yet, and I, of course, don't know everything, but I haven't really seen the backdrop to these variations, and I was wondering what they are.
Well, as far as sea level is concerned, it pretty much has been a constant rise since it first began to be measured. There hasn't been much of an acceleration at all anywhere. And you can actually go that, there are sea level, there are sea gauges, tide gauges at all kinds of places, all kinds of cities on the coast. You can go there and they have a long record of sea level at that spot, San Francisco, for example. And you can actually get that on the web and look at the graph yourself. And what you see is that it's just straight slope all the way from when they first started measuring, back to 1900 or back to 1850 or whenever they started measuring the tidal flow there. And the typical sea level rise is measured from satellite these days. And sometimes the satellites wear out and they have to put up another one. And maybe the instruments change a little bit. And so the calibrations change a little bit. And so there are bumps and people have to be careful about that. But by and large, there just hasn't been any particular change in sea level rise, in the rate of sea level rise, for probably 100 or 150 years, as far as anybody can tell. And there are
there's really been no extra sea level rise in 100 to 150 years.
Yeah, it's been rising. Sea level has been rising, but the rate of the rise is quite small. It's a couple of millimeters a year,
Okay.
which isn't much. And it's been pretty much a couple of millimeters a year ever since they started measuring it.
How about for CO2 concentration in the air or NOx, SOx, et cetera? What about those concentrations for carbon?
Well, carbon dioxide, of course, has gone up, right? We know that in 1900, it was at about 295 parts per million, something like that. And now it's at about, 420. So it has gone up. But the only observable effect that carbon dioxide has had on the Earth that we know about, that we can observe, is that it's caused the ecology to green up all across the world by about 15% since 1980. So all the forests.
Oh, wow. So more green means more conversion of carbon dioxide into oxygen. So maybe it's a countervailing force?
Well, what's happening is that maybe you don't know this, but at 295 parts per million, which is where it was in the year 1900, that's semi-starvation levels for plant life. Plants take up carbon dioxide to produce the cellulose of their stems and trunks, and also to make all of their secondary metabolites that they need, and so on. Carbon dioxide is their only source of carbon, and they have to take it up from the air. And at 295 parts per million, plants have a hard time getting the carbon dioxide they need in order to grow. And and during the ice ages, carbon dioxide levels in the atmosphere fell to 185 parts per million, much less than even at the year 1900. And that's real starvation levels. And at 120 parts per million, photosynthesis turns off. And at 90 parts per million, all the plants die. So Earth was really skating the edge of disaster during the last 7 ice ages when carbon dioxide fell to 185, 190 parts per million. Plants were really kind of holding on to the edge there. So the fact that...
A quick question. So there's 2 scales you gave me from 1900. We have an anchor of 290 parts per million. What about 1800, 1700, 1600? If we go back, ice age, what kind of variation has there been?
The carbon dioxide started going up again when the last ice age ended 12,000 years ago, because the oceans warmed up. And when the oceans warm up, they outgas the carbon dioxide that's dissolved in the ocean water, and it goes back into the atmosphere. And so the carbon dioxide level in the air rose after the end of the last ice age, and the climate all warmed up, including the oceans. And so even, say, 5,000 years ago, carbon dioxide was still somewhere around 295 parts per million, thereabouts, plus or minus 10, say.
Well, what about before? The last ice age? What did it look like? And was there times in Earth's history that we can discern where carbon dioxide was, above 300, 400, 500 ppm?
Oh, absolutely. I can just pull this right up. I have a CO2 over geological timescales map right here. Say about 15 million years ago, CO2 was up at about close to 500 parts per million or so. And 140 million years ago, it was about 1,000 parts per million. So, there's been times in the past when carbon dioxide has been a lot higher than now. And in the really distant past, of course, Earth had an entire carbon dioxide atmosphere, 60 bars of carbon dioxide. So that means 60 atmospheres of CO2 in 4 billion years ago. And it's been declining ever since.
How do you translate atmospheres into parts per million?
Well, one atmosphere is a million parts per million, right? So right now, the oxygen is about 21%, thereabouts. So that would be 210,000 parts per million. And nitrogen is about 80% of the atmosphere. So that would be 800,000 parts per million. So way back, say, 4 billion years ago, when Earth first formed, it had an atmosphere that was 60 times heavier than the atmosphere is now. And that means 60 times more gas. And almost all of that gas was carbon dioxide. And there was a little bit of nitrogen.
But, if we don't go back quite as far, if we go back 20, 30, 40,000 or 100,000 years ago, what were the CO2 levels? Let's say over the past million years, what was the range of parts per million CO2 levels?
Yeah, the range of over the last million years, when we had 7 ice ages over the last million years or so. And the range of carbon dioxide during those years was probably about 190 parts per million during the ice age, and 295 or 300 or so parts per million during the intervening warm period.
So were the intervening warm periods as long as we've had now, about 12,000 years or longer?
Yeah, about that. Yeah.
Oh, okay. So we haven't really seen, if we had a period of, let's say, 50,000 years with no ice age, do you think that the CO2 in the atmosphere would rise as high as it is now? Or do you think there's other factors contributing?
We're putting carbon dioxide into the atmosphere. There's no doubt about it. So what's happening is that carbon dioxide is slowly being removed from the atmosphere by carbonate precipitation and subduction. That's why the huge amounts of CO2 we've had in the past have all disappeared. All the White Cliffs of Dover is all carbonates that used to be carbon dioxide in the atmosphere.
What about with additional greening? There should be additional sequestration of CO2, like you said, to build the parts of the plants, secondary metabolites. So what is the biomass sequestration number?
Well, approximately half of the CO2 that we put into the air by burning fossil fuels has disappeared into the plant life. So only about half of what we produce actually shows up in the air. The rest of it probably gets taken up by the plants and also probably by bacteria in the soil, photosynthetic bacteria.
But it sounds like maybe not all of it's being taken up. Could that be why CO2 levels are rising, or what do you think?
Sea levels are rising because we're in an interglacial period and the oceans are warming up. And so the ice caps are melting some, and the ocean water warms up, it expands. And so part of the sea level rise is just the thermal expansion of the ocean because it's getting warmer because we're in a warm period right now. So a combination of the melting ice and the warming of the ocean is responsible for pretty much all of the sea level rise.
If we don't have another ice age, what do you think will happen over the next, several hundred, several thousand years, really?
Well, if we don't have another ice age, then things stay, pretty much as they are now. Carbon dioxide, if we stopped putting it into the atmosphere, would start to, slowly overturn and begin to decline over a period of thousands of years. And honestly,
I mean, if there's no ice age, okay, right. What would happen if we just cease to exist and there's no ice age? What would happen to the carbon levels, and what would happen if we just continue on as we are and there's still no ice age? What under those two scenarios? What do you think?
If humans all disappeared, you're saying, and there was no ice age, what would happen? Is that pretty much it?
Well, the two scenarios. One is humans magically disappear and there's no ice age. Okay. Another one is we're here, nothing special happens. We keep putting CO2 in the atmosphere and there's no ice age either. What would happen under both scenarios?
All right. So the first one, humans disappear and things continue on as before. Then no more carbon dioxide is put into the atmosphere because there's no more fossil fuel burning. And what would happen is over a very long period of time, the carbon dioxide in the atmosphere would slowly get used up, not from the plant life because that recycles carbon dioxide, but because it dissolves into the ocean and gets precipitated as carbonates and gets subducted and turned into rock. And if we weren't here, eventually the carbon dioxide would, descend back down to 295 and continue on down and eventually get to, 180 and then 120 and then 90 and then all the plants would die. So that's actually the most likely scenario under ordinary circumstances of what would be the end of life on Earth is all the carbon dioxide would get used up, plants would all die, and the food chains would all collapse. So your other notion is that we're here, we continue to burn fossil fuels, carbon dioxide continues to go up, what happens then? So that's the interesting question as far as climate models are concerned. Setting aside climate models, there's no evidence that carbon dioxide has done anything to air temperature. There's no actual physical evidence that carbon dioxide has actually done anything to air temperature. And so my best guess is that if we're here and we keep pumping carbon dioxide into the air and it gets up to, say, 1,000 parts per million or so, all the plants would be really, 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 really happy and nothing else would happen. There would be no particular change in temperature due to that. And let me expand on that for just a second. The reason that I can say that with some confidence is that carbon dioxide has gone up and down during all 7 of the past ice ages over the last million years. And temperature has also gone up and down during those ice ages. The ice age starts, temperature goes down and CO2 goes down. And then, after 100,000 years, the ice age comes to an end and the Earth warms up and then carbon dioxide goes up and temperature goes up. But in every single case that we know about of the 7 ice ages, it's always the temperature that goes up first and then carbon dioxide follows. And then when carbon dioxide is high, the temperature starts going down. And then carbon dioxide follows and starts to go down about 800 years later or so. So to put that succinctly, in every single case, temperature leads carbon dioxide. Carbon dioxide never leads temperature. It's not like CO2 goes up and it causes the temperature to rise. It's not like that at all. It never happens that way. It's always the temperature goes up and then CO2 goes up. So that's actually very, very embarrassing. That discovery is very embarrassing to climate modelers because they would have predicted exactly the opposite. So it kind of falsifies their point of view. Been very quick to make all kinds of hand-waving excuses for why, the carbon dioxide was important anyway, and so on. But in fact, there's no evidence that carbon dioxide had any influence on temperature at any time that we can resolve in the past. So, I think it's going to be like that in the future, too. If CO2 goes up to 1,000 parts per million, all the plants become really, really happy, and the temperature pretty much stays the way it is now.
So who and how are they making the link to carbon dioxide and temperature?
I had an interesting exchange with a climate modeler who will remain nameless because I'm a charitable kind of guy. And we had a go-around, a very short one by email about that exact question. And he wrote and said, well, isn't it your expectation that if carbon dioxide goes up, the temperature should go up? And I replied, I asked him whether an expectation is the same as a quantitative prediction. And he disappeared. That was the end of the conversation. I never got a reply. So that's the way it is. They've put their expectations into the climate models. But it's not a physical fact that carbon dioxide causes direct increases in air temperature. It's just built into the models because it's an expectation of the modelers. Yeah, curious.
Yeah, that's no. So what would be the mechanism by which increased CO2 would cause all the problems and the warming that they say is happening?
Well, the inference is based on radiation physics, which is completely correct. The radiation physics of carbon dioxide is completely correct, and I can explain that in direct terms that are readily understandable, and that is that carbon dioxide absorbs infrared radiation. Typically, the way that the system works is that the radiation comes down from the sun, and it's shortwave, and it heats up the surface of Earth. And the surface gets warm, and it radiates thermal energy, infrared energy, back up because that's, infrared is heat. And carbon dioxide can absorb some of that heat and become an excited molecule. It means that it starts vibrating, that, it's a carbon in the middle and oxygen's like little wings, and they all start vibrating really fast after they absorb this energy. And so you have an excited molecule, and that molecule bangs into nitrogen and oxygen, gaseous molecules in the atmosphere, and transfers some of that energy that it's absorbed into the oxygen and nitrogen molecules and makes them zoom around more quickly. It increases their kinetic energy. And kinetic energy is the same as heat, the heat that you feel. So in principle, carbon dioxide can make the atmosphere hotter by changing radiant energy into kinetic energy by this mechanism of getting excited by absorption of infrared radiation and transferring that energy by bumping into nitrogen and oxygen. But the question then is, what happens to that kinetic energy? Does it really cause the temperature to rise, or does it cause evaporation to increase? Or does it change the convection rate? Or does it make things windier? Or does it cause more clouds to form? Earth has a large number of very fast reaction channels that accommodate all kinds of energy in all kinds of weird ways that are not well understood. So even if carbon dioxide injects kinetic energy into the atmosphere, which it does, there's no reason to think that kinetic energy will show up as sensible heat. Sensible heat is the heat that you can feel and you measure with a thermometer.
Yeah, but again, if you look at the effects of the sun's radiation, on the Earth, does that dwarf the potential increase in kinetic energy and thermal energy based on carbon dioxide having,
of course it
more
does.
Prevalence? Okay.
Yeah, of course it does. It's an interesting thing. I remember way back when this controversy was more in the forefront, in fact, than it is now, back in the 2000s, somebody made the case that putting more carbon dioxide in the air is like putting a 1-watt bulb on every square meter of Earth everywhere, all over Earth. Every square meter gets a 1-watt bulb. And he says, that's the effect that we're having. And that sounds pretty scary. It's a lot of energy, and every square meter's got one. But then you realize that every square meter already has 245 little 1-watt bulbs there. And so now when you add carbon dioxide, it's 246. So, what's the big deal? It's less than 0.5% change. So
How long have you been examining the data, and what it looks like instead of just CO2 increasing, it looks like the politicization, ppm, the parts per politicization have been increasing. What have you seen that? How have you seen that manifesting, and over what time period?
Well, I mean, that's essentially been manifesting since the 1980s, really. Before in the 1970s, everybody was worried about global cooling because we were at the end of a long cooling period from the 1940s. And there were people who were talking about the new ice age and so on. And then things swapped around. There was something called the Charney Report that came out, I think it was in 1976, that talked about the warming potential of carbon dioxide. And it was debated in the literature sometime before that. And it was realized that very small changes in cloud cover could make invisible any thermal effect that carbon dioxide could have, so that there would be no change in the obvious heat. So it's only a couple of % change in cloud cover. So then the Charney Report came out, and it alerted everybody to, oh boy, there's a problem here. And then in 1989, when James Hansen gave his testimony before Congress, that's when it really became politicized. He made this very alarmist projection that climate change was already upon us, and that it was a hot June day in Washington, D.C., and that hot June day was manifestation of the global warming that was already upon us. And Hansen gave a statistic that said increase in temperature since 1950 or so was already 3 sigmas above the natural variability, which he couldn't have known, but he had a number that showed that. And after that, the New York Times got a hold of it, and off it went, and it became politicized ever since. And there have been some funny things, very awful things that happened. For example, the second assessment report that came out from the IPCC got modified after all the scientists had signed off on it to make it seem like there was discernible human influence on the climate that, in fact, the original report did not say. And Frederick Seitz, who was past president of the American Physical Society, protested against this adulteration of the IPCC report, the second report. He was vilified, and called a tobacco an aficionado and all kinds of awful things to try and ruin his reputation so that his criticism would not have any force. So it got politicized. That was back in 1995. So it got politicized very early.
That's crazy.
Yeah.
What are some other major talking points that you looked more deeply into to see, perhaps the same or different story?
I've looked into the whole thing, actually. The first thing I looked into was the climate models based upon this paper that I mentioned by Willie Soon and Sally Baliunas and their colleagues, and looked at the errors that the models make with respect to the amount of heat energy that's in the atmosphere, and found out that the errors they make are much, much larger than the impact of carbon dioxide. And so there's just no way that they could resolve that effect. And essentially the IPCC is talking through its hat. But then I looked further, and I started looking at the air temperature record when I discovered from the papers of the people who compile that record that they assume that all the errors are random and average away into zero. And that didn't make any sense to me, speaking as an experimental scientist, because you don't just get random errors that go away. You get systematic errors where the instrument isn't operating properly, or there's been a mistake made, or the calibration is poor. And so I looked into that, and it turned out that the people who compile the record pay no attention to the serious errors that creep into the air temperature record, because the sun is shining on the boxes that hold the thermometers. You have a meteorological station out there someplace, and it's a louvered box. It's a wooden box with louvers on the side so the breezes can blow through it. It's got some thermometers inside, and that's where they record the air temperature. But the sun is shining on that box, and if there's not enough air that's flowing through that box to bring cool outer air into the interior of that box, the temperatures that it records are too warm. And if it's a cold winter night and a clear sky, the box can radiate its heat energy into the sky and become colder than the surrounding air. And then the thermometer registers a temperature that's too cold. And these errors are significant compared to the changes in air temperature due to over the period of the last 150 years. And so I went through and I did a detailed analysis of that, and it turned out that the uncertainty in air temperature is at least plus or minus half a degree Celsius. And when you talk about a change in air temperature since 1900 of about 0.8 of a degree, it's now 0.8 of a degree plus or minus half a degree. And you look at the numbers that they talk about, and they say it's 0.8 of a degree plus or minus 0.025 of a degree. They give a surety to their work that their numbers just don't have. So you get the impression, I got the impression after studying this for quite some time, the air temperature record, that the people who are compiling the record have never ever operated an instrument. They have no idea how hard it is to struggle with an instrument to get good data and to reduce the amount of systematic errors to the point where you can believe your numbers. They seem to have no concept of that. Just as well, let me tell you,
Okay.
This has been the big revelation to me, is that none of the climate scientists that I've dealt with, except for a couple, have any concept about how to establish the reliability of their own data. And that includes the climate modelers, who don't even know the difference between precision and accuracy. That's about as fundamental a thing to know in the experimental or any sciences as it's necessary to know. The difference between the correct answer and to an answer that repeats itself every time you make a measurement. Those are two different things. You want to have an instrument that's reliable and gives you the same number every time. That's precision. But if you want it to give you the same answer, that's the right answer every time. And that's
like a broken clock is right twice a day.
Well, there is that, yeah. When you have a watch, and you look at it, and it says at the same time of every day, it says 1 o'clock, but you know that the time is 10 a.m. It's precise, but it's not accurate. And they don't know the difference between those two things. And it took me 6 years to publish this paper on climate model error. 6 years and 13 submissions and 35 reviews that I had to deal with.
Oh, what was that like? I know. Make the sign of the cross before you answer.
Yeah, it was a real saga, and I had to persist. But what I discovered was, in these interactions with the reviewers, nearly all of whom were climate modelers, is that they knew nothing about how to analyze the reliability of their own data and the reliability of their own model output. They don't know how to do it. It's like they're not trained in it. And because of that, their papers, which look very mathematical and wonderful with all kinds of graphics and, uncertainty bars and this and that and something else, it all looks like science, but it isn't science. It's all just statistics. And the error bars that they give are all what's called precision, because what they do is they publish the variation of their models, their model outputs versus its own average. And that doesn't tell you anything about what the right answer is. It only tells you that the model will repeat its own projection successfully. That's all.
Wait. They're comparing, to justify, they're comparing the model versus the model?
Yes, exactly. So, you take a model and you run it 10 times, or you take 10 models and you run them all once. And then you take the average of all the runs, so you have a single line, and then you take the spread of the individual lines around that single line and you say that's the error. But of course, it's not the error. That's just the model output spread. And the real error is, the difference between the output and the correct answer. That's the real error. And they have no concept about that. None of them. I've yet to meet a climate model who understands the first thing about how to analyze error. And that explains a lot about why this alarm has been so persistent, is that we're dealing with people who are, I'm sorry to say it, and I'll say it's my opinion so that nobody gets sued. We're dealing with people who are incompetent. They're incompetent as a class. I've never run across that before, but there it is. My opinion, my considered opinion, I'm ready to defend that opinion, and I've got 50 megabytes of evidence showing that opinion is correct. So that's
why do you think this has become so politicized, and why is it so alarmist? What's the driving forces?
I've been struggling with that conundrum for years now, and between you and I and whoever's listening, probably, one other guy out there somewhere. I'm not denigrating you, I promise.
No problem.
Yeah, I've wondered this for years. I've talked to physicists and they run away from the question. And the American Physical Society should have stepped up and done a good analysis and said, look, they're not talking about accuracy here. They're not talking about reliability. We can't trust any of the things that they're saying to be true. But the American Physical Society has been silent. And in fact, they've been recalcitrant when they've been challenged. So, I blame the scientific establishment for allowing this to continue. It's their fault. The National Academy of Sciences should have stepped up, but they haven't. They've encouraged it. And for reasons I don't understand. I just don't understand it. It could be, I think it was Timothy Wirth, the senator, who said that even if the science is wrong, we have to go with it because we're doing the right thing. So it could be noble cause corruption. I don't know. But for whatever reason, the American Physical Society has been silent. The American Chemical Society has been silent. All the scientific official bodies, institutions, they've been silent. They've actually contributed to the alarm. They've been recalcitrant when they've been challenged. National Academy the same way. And so, I've never had an opportunity to talk to them in private and find out what's going on. I knew a guy, I won't say his name again, who was the president of the American Physical Society. And I wrote to him, I sent him the link to this paper on climate models that I published and pointed out that climate models can't tell us anything about the climate and asked him to do something about the position that the American Physical Society took on it. And he said he'd look into it. And then there was nothing. I heard nothing back. So I sent a follow-up email, and it was received.
Was he found dead somewhere, or what happened?
No,
suspicious circumstances.
No, I'm sure he's still around. But his responses after that were silence. He never responded. That's what I find over and over again, is that people just do not respond. And so I have no idea what's going on, what kind of pressure is being brought to bear, if it is, or whether they, feel like they need to push the issue because it's the right thing to do, even if the science isn't there. I just don't know. It's one day maybe we'll be able to find out after it all collapses and everybody comes to their senses.
Yeah, I don't know. That's kind of crazy.
It is crazy. Yeah, it's literally crazy. I mean, it's rational insanity is what it is.
I don't know. Like, what's your projection on what's going to actually happen to the Earth and the climate over the next, let's say 50 years?
Well, there's no reason to think the climate's going to do anything that it hasn't done in the past. And whatever is going on now in the climate, I mean, everything that we can see, the extreme weather, the hurricanes, the tornadoes, the droughts, the floods, all of that stuff, it's all within natural variability. There's nothing unusual going on, including the recent warming. It's not unusual at all. It's been warmed in the past and then cooled again. We know of at least 4 prior warm periods before ours, the medieval warm period, the Roman warm period, the Minoan warm period, and then we have the Holocene optimum, which occurred about 8,000 years ago, which was upwards of 2 degrees warmer than it is now. And nothing bad happened. If anything, life prospered because everything was warmer. And nothing that's happening now, including sea level rise, is unusual from a climate perspective. So there's no reason to think that anything weird is going to happen with the climate over the next 50 years or 100 years or 1,000 years. It's just, going to go on into the future the way it has done in the past. And whatever we have done with carbon dioxide doesn't seem to have any discernible effect at all. None. Zero.
So where would people find a good summation of the points we talked about? Is it in a book? Is it in various papers? Like, what would you recommend? Well,
I can recommend this paper that you took notice of in our email communication, which is the Negligence, Non-Science, and Consensus Climatology paper that I wrote. It's not a qualitative paper, but it's relatively straightforward. And it covers all 3 legs of the climate alarm problem. It covers climate models. It talks about these paleo air temperature reconstructions, and which we haven't discussed, and it talks about the global air temperature record and the error that's in it, and shows, so when it talks about climate models, it talks about the errors that they make, and then it shows how badly climate models miss out when you try to project their temperatures across 100 years. That the error bars at the end of 100 years is plus or minus 15 degrees. And so, so you can't really say, well, what's going to happen in 100 years? Well, carbon dioxide is going to make the Earth 3 or 4 degrees warmer than it is now. And you say,
well, I hear all the time, the difference between 1 degree and 2.5 degrees is disaster. And, so they're talking on that scale, not 15 degrees.
Yeah, well, the 15 degrees is an uncertainty. It's not a real temperature. Right. That's the width of ignorance over which the models are operating. It's like, if I can make a quick analogy, it's like some guy is drunk and he's driving home and he decides before he goes home he's going to walk in the woods. So he parks his car, then heads on out and disappears. And if he's gone for 1 day, you have a certain area that you can check. It's a semicircle from where he started. But after 3 days, the semicircle can get a bit much bigger because you don't know how far he's wandered off. And if he's gone for a week, you've got a huge area that you have to search. So that area is an area of ignorance. You don't know where he is anywhere in there. And so you can't say that he's walked all those square miles, but he's disappeared inside them. And it's exactly that with the climate models. We know that there's going to be some air temperature in the year 2100. But as far as the climate models are concerned, the width of their ignorance about where that temperature is going to be is so huge, 30 degrees wide, that they're not telling us anything about what the temperature could be back in 100 years. It's like somebody saying, well, he walked into the forest and we know that he's in there within 100 square miles. Well, that's not going to help anything.
Right.
Yeah. So it's like that. It's like that. It's just this huge width of unknown temperature, and they have no idea where the correct number is inside there. But it won't be 15 degrees. It'll be a couple of degrees this way or a couple of degrees that way, if that.
Right.
More like a tenth of a degree this way or that way. And none of it's going to be any different than what happened in the past, as far as we can tell.
Well, very good, Patrick. So, again, best place for people to go to get more information that are listening is where? Let's repeat that, and then we'll close.
Well, I'll tell you what. Do you guys have a website where people can access information?
Yeah, we have findinggeniuspodcast.com where people can go, and we'll put this in the show notes. So where should they go?
I can send you, if you like, an op-ed that I wrote for a Swiss magazine that discusses the climate model issue for the intelligent non-specialist. And I think it will really bring home the uncertainty issue and the lack of knowledge issue that surrounds the climate alarm, that will allow anybody who wants to read that to have a very intelligent perspective on what's going on. And it's also reassuring because it tells people that they can anticipate a wonderful future for their children, and it's not going to be some thermal Armageddon that's going to kill them all.
Well, very good. Yeah, we'll include that in the show notes. So,
okay,
Patrick, thanks so much for coming on the podcast. I appreciate it.
Okay, thank you very much for having me.
Remember, before you go, supplementing with hemp CBD products is one of the best things you can do for your well-being. Get your CBD from a company that cares and offers you holistic support in your healing or wellness journey. Feel Good Hemp is giving our listeners 33% off their first purchase. You can use coupon code GENIUS33 at checkout to save 33% site-wide. Visit feelgoodhemp.org to shop now and access their free empowerment platform.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.